Hi, everyone. So last time we took a look at the idea of an indefinite integral, and we looked at some of its properties. But now we're going to be looking at some more examples on how to solve these indefinite integrals. Okay, so let's start off with example number 1. So we want to calculate the integral of the fourth root of x to the 5. Okay, as it is, looks pretty complicated. However, using our surd to exponent rules, we can turn this into a nice exponent form. So we can write this as the integral of x to the 5/4 dx. Now that we've got an exponent, we can easily use the power rule for antiderivatives. So if we add 1 to the exponent, we're going to get 9/4. Then dividing by 9/4 is the same thing as multiplying by 4/9. So we get 4/9 x to the 9/4. And don't forget the plus c. Okay, because we want the whole family of antiderivatives. Okay, not just one. Okay, number 2, we have the integral of 5 plus 2/3 x squared plus 3/4 x to the 3 dx. Okay, now this is just a standard polynomial with simple powers. So we just apply the antiderivative rule to each term. So for the first one, we're going to get 5x. For the second one, we're going to get 2/9x cubed. For the third one, we need to divide by 4. So we get 3/16x to the 4. And don't forget the plus c. Okay, so that's pretty straightforward. Let's look at the next one. Number 3, we have the integral of x to the 6 minus 2x to the 5 minus x cubed plus 2/7 dx. Again, this is just a straightforward polynomial, so we can apply the antiderivative rules to each term. So for the first one, we're going to get 1/7x to the 7 minus 2/6x to the 6 minus 1/4 x to the 4 plus 2/7x, and don't forget the plus c. Okay, and just a note here, we've got 2/6. You can simplify that if you want to 1/3. Okay, number 4. We have the integral of x squared plus 2 squared dx. Okay, this doesn't look like a standard polynomial, so looks pretty complicated. Later on, we will see that there are other methods of solving this. Okay, so we'll do that next week. However, for now, we are stuck with just expanding everything out into a polynomial and then applying the power rule as we know it. Okay, but later on we will see that there are simpler approaches to this. Okay, so let's just expand this out. So we're going to get x to the 4 plus 4x squared plus 4 dx, and then we need to multiply the x throughout. So we're going to get the integral of x to the 5 plus 4x cubed plus 4x dx. And now we can apply the antiderivative rules. So for the first one, we add 1 to the exponent to get 6, and we divide. So we get 1/6 x to the 6 plus x to the 4 plus 2x squared, and don't forget the plus c. Okay, so it started off looking pretty complicated, but once you expand everything out, then it's just a normal polynomial that you can then apply the rules to. Okay, but remember what this looks like, because we will be seeing more things like this later on. Okay, number 5, we have the integral of the square root of t t squared plus 3t plus 2 dt. Okay. Now, like I said before, these integrals here, this variable that we use doesn't really matter. So here we've just replaced x with t, but we are integrating with respect to t, so we just do it as normal. Okay. Just looks different. So here again, it looks a bit complicated, but again, we just have to expand it out, and then we will get a nice sum with powers. Okay, but before we do that, the square root of t, we need to write it with an exponent. So we can write this as t to the 1/2. Okay, that works a bit better when we're multiplying this out. And then, of course, when we have to use the power rule, we need exponents. Okay, so let's multiply this out. T to the 1/2 times t squared. We need to add those two together. So we get t to the 5/2 plus 3t to the 3/2 plus 2t to the 1/2 dt. Okay, so now everything has a nice exponent. We can then apply the power rule for antiderivatives. So adding 1 to the first power gives us 7/2. We need to divide by that. So we get 2/7 t to the 7/2 plus, it's going to be 3 times 3/2 plus 1 will be 5/2. So it will be 6/5. So that's 3 times 2/5, so it's 6/5. T to the 5/2. Plus, again, we add 1 to the exponent to get 3/2. Dividing by 3/2 is the same thing as multiplying by 2/3. But we've got another 2 here, so it becomes 4/3. T to the 3/2. And don't forget the plus c. Okay. So that's example number 5. So you see, it may look complicated in the beginning, but if you just write things in terms of powers, you expand everything out nicely, then it's just the power rule. So it's not too bad. Okay, but if you do have any questions, again, please, you can email me whenever you like, or you can post a message on the class WhatsApp group. Okay, and then I'll respond as soon as I can. Okay, let's take a look at some more examples. So we're on example number 6. We have the integral of 1 plus the square root of x plus x all over the square root of x dx. Okay, again, this looks really complicated. We've got square roots of x and we've got fractions, but we can just expand this out and we'll end up with something nice and simple. So if we expand this fraction, we're going to get 1 over root x plus root x over root x plus x over root x. Okay, so when integrating things like this, we like to have individual terms so that we can apply the rules to the terms one by one. Okay, rather than having one complicated fraction. Now, if we remember that the square root of x is the same thing as x to the 1/2, we can rewrite all of these using powers. So here we're going to have x to the minus 1/2 because it's in the denominator. This next one's just going to be 1, and the next one's going to be x to the 1/2 because we have x to the 1 divided by x to the 1/2. So 1 minus 1/2, we're left with 1/2 dx. Okay, so now we apply the rule. We add 1 to the exponent and then divide by the new exponent. So if we add 1 to the first exponent, the new exponent is going to be 1/2. Dividing by 1/2 is the same thing as multiplying by 2. Okay, antiderivative of 1, that's going to be x. Next term, we add 1 to the exponent, so we're going to get 3/2. Divide by 3/2 is the same thing as multiplying by 2/3. The new exponent is 3 over 2. And don't forget your plus c. Okay, so we started off looking a bit complicated, but you just expand out, make everything have nice powers, and then apply the rules. So it's really not that complicated. It just looks a bit complicated at the beginning. Okay, so that was example number 6. Let's take a look at number 7. So we have the integral of x cubed minus 2 root x all over x dx. So this is very similar to the one we just worked on. It looks like a complicated fraction, but we can separate everything out and write it using some powers. Okay, so x cubed over x, one of the x's are going to cancel, so we're left with x squared, minus, we're going to have root x, which is x to the 1/2, divided by x, so it's half minus 1, it's minus 1/2, so we're left with 2x to the minus 1/2 dx. Okay, so now that it looks much simpler, we can then apply the rules. So for the first term, we add 1 to the exponent to make it 3, divide by 3, so we get 1/3 x cubed. Minus, we add 1 to the exponent to make it a half. Dividing by a half is the same thing as multiplying by 2. So we have 4x to the 1/2. And don't forget your plus c. Okay, so this is the typical type of question you're going to get where you have to apply the power rule. But remember, there's not just power rules, there's also trig functions that we have to deal with. So these next couple examples are going to be on trig functions. Okay, so this is number 8. So we have to take the integral of 2 plus tan squared x dx. Okay, so now 2, that's easy. That's just going to give us 2x. But tan squared of x, there's no simple, antiderivative for tan squared. So we need to work a bit on it. Okay, so we know that tan can be written as sine over cosine. So let's try that and see where we get. So we're going to have 2 plus sine squared of x over cosine squared of x dx. Okay, so it looks a bit more complicated now, but remember that sine squared of x can be written as 1 minus cosine squared of x. So now we write everything in terms of cosine. Okay, so maybe that will help. So we have 2 plus 1 minus cosine squared of x over cosine squared of x dx. Okay, it looks like it's getting a bit better because now it's all in terms of cos. So let's separate things out and see what we get. So 2 plus, we're going to have 1 over cosine squared of x minus 1. Okay, because cosine squared over cosine squared, that's just going to be 1. Okay, but we got the minus sign. So this we can write as 2 minus 1, that's going to be 1. 1 over cosine squared, that's going to be sec squared of x, which is great because we know the antiderivative of sec squared. And we also know the antiderivative of 1. So this is going to be x plus tan x, and don't forget your plus c. Okay, so let's just go over this again. We saw we've got a tan squared, so that's a bit complicated. We can't handle tan squared from what we know, but we can manipulate it with a bit of trig identities until we get to something that we do know, and that is sec squared of x, because we know the antiderivative of sec squared is just tan. Okay, so sometimes you need to use your trig identities to manipulate what you've got into something that you can then easily find the antiderivative of. Okay, but as you can see, it's not much work to get to where we need. Okay, we've got a couple more problems here. Okay, a bit more on trig problems. Oops, sorry. Okay, so number 9, we have the integral of sec x into sec x plus tan x dx. Now, as it is, this is complicated to do because it's a product of two functions. We don't know how to deal with that just yet. But remember what I said, if you're in doubt with what you need to do, try and multiply everything out so that at least you can work with individual terms, because the whole might be complicated, but each individual term might be easier to solve. So let's see if that principle works here. So this will be the integral of sec squared x, okay, that's looking promising, plus sec x tan x dx. Okay, now this is much better because the integral of sec squared of x, that's known, and the integral of sec x tan x, that's also known. So this first line was complicated because it was a product of functions and we don't know how to deal with that. But we multiplied it out, we got two individual terms, and each individual could be done separately. So let's do that. So the integral of sec squared, that's just going to be tan x. And the integral of sec x tan x, that's just going to be sec x. And don't forget the plus c. Okay, so please remember this principle. If the product of functions looks too complicated as is, try and multiply it out and look at the terms individually. Okay, so maybe each smaller problem will be easier to do than the overall larger problem. Okay, let's look at the next one. Number 10. So we have the integral of 1 minus sine cubed of x over sine squared of x dx. Again, this looks pretty complicated because we've got powers of trig functions and fractions going on. But if we just separate things out into individual terms, we will see that each part is actually pretty easy. So for the first bit, we're going to get 1 over sine squared of x. And for the second bit, we're going to get sine cubed divided by sine squared. So there's going to be a sine of x left over. Okay, now 1 over sine squared, we've got another trig function that represents that, you know, the reciprocal trig functions. So we can rewrite this as cosec squared of x. And then we have the minus sine x dx. So remember, 1 over cos is sec x, 1 over sine is cosec x. Okay, those are the reciprocals. Okay. Now, each of these can be done quite easily. The integral of cosec squared of x, that's going to be minus cotan of x. And the integral of sine x is going to be minus cosine x. But we've already got a minus there, so it's going to be plus cosine x. And don't forget the plus c. Okay, so again, if you look at the beginning, it looks quite complicated. But if you separate things out into individual terms, you may see that the individual terms are easier to solve individually than as a whole. Okay. Okay, so just remember that principle when you're going through these problems. Okay, last question for today, number 11. We have the integral of sine 2x over sine x dx. Okay, this looks pretty complicated because we've got this fraction going on. But if you remember your trig identities, this top term should be shouting at you, because remember sine 2x, that's one of your double angle formulae. We can rewrite that as 2 sine x cosine x. So 2 sine x cosine x all over sine x dx. Okay, so whenever you're in doubt with trig functions, just think to yourself, what are the trig identities that you know? And then, you can use those to simplify what you're given. Okay, like in this case, because we've got a sine x from the sine 2x, and we've got a sine x at the bottom, they're going to cancel each other out. Okay, so we're left with the integral of 2 cos x dx. Okay, this 2 can be taken out because it's just a constant. Okay, so now we need to find the antiderivative of cos. That's going to be sine, because remember, the derivative of sine gives you cosine. So the antiderivative of cosine will then be sine. So this is going to be 2 sine x. And don't forget your plus c. Okay, so these were just some typical examples that you should know. Okay, so don't worry too much about the specific examples. Your test will have something different, but I want you to understand the principles that you learn by doing these examples. Okay, so your test will have something completely different, but it's the same ideas. So if you have a trig function that's complicated, use the trig identities to simplify it. Or if you're given some fraction, maybe you can separate it out into individual terms. Or if you're given a product of things, maybe if you multiply them out, you will then get individual terms that are easy to find the antiderivative of. Okay, so those are just some principles that you should keep in mind. Okay, later on, we will look at more complicated integration techniques, but those are used for more complicated functions. Okay, and you'll see straight away when it's a very complicated function and you need to use the trig techniques, the integral techniques, or if it just looks complicated, but in fact, you can just expand it out a bit and then it becomes simple. Okay, but that just comes with practice. So please go through the next tutorial. There's plenty of problems to go through. And then we will have a look at those problems on Wednesday next week. And remember, Wednesday next week, we've got the tutorial test. And this time it is written. Okay, so it's not going to be that MCQ quiz that we had last time. Okay, it's actual paper and pen problems. Okay, but if you have any questions at all, please email me. You've got my email address, or you can post your questions on the class WhatsApp group. Okay, I'll see you in the next lecture.